In this video, I want to go over several examples of least squares regression problems where I will take them from the statement of the problem to a solution. Just a few heads up. The first thing I would say is that this is going to be a bit of a long video because of the number of examples I'm doing. My guess is that for most uses, you won't actually want to watch the whole video. That is, you may want to look for a problem that looks as similar to what you're doing and watch my video of that problem and not the entire thing. The second point I want to make is that if you were actually doing least squares regression in a real application situation, you shouldn't really be doing it by hand, I guess. So in this video, I'm going to use software, but I'm going to define matrices, multiply matrices. In Python, there are built-in packages that can do this for you. And so if you actually find yourself needing to do regression in a real situation, you should be using those packages and not doing it by entering in matrices. That said, we're approaching this from a linear algebra perspective, so we're actually going to calculate these numbers using the matrices, and we'll get the exact same answers that you would have gotten if you did this using one of those software packages. All right, so the first problem I want to look at, actually, I guess I'll give you just a summary. This first problem is going to be a very abstract problem where I'm looking at a matrix equation with no solutions, and I'm trying to find a least squares solution. The second problem I'm going to go over is the example from the conceptual video, where I'm trying to predict students' exam scores from their quiz scores. In a third example, I'm going to give another application problem where instead of a linear model, I'm looking at a cubic model. So I'll show how what we've done can be applied to equations that aren't just linear. And then in the final example, I'll look at a multivariable example where we have multiple variables that we're trying to use to predict the value of another. And again, we apply the same things we've been doing in that situation. All right, so this first example is what I call the abstract example because we have no context, right? We're just given a matrix equation that has no solutions. It's not surprising that this matrix equation has no solutions, right? Because we have more rows than columns. In general, we expect that we might have no solutions. We could have solutions if there's some redundant information, but we might have conflicting information. So this thing doesn't have any solutions. And to see why it doesn't have solutions, we can look at a picture of what's going on. So I'm gonna draw in the columns of this matrix. So here, these two vectors are the columns of the matrix. And see them here. And any solution to the equation ax equals y, in order for there to be a solution for a given y, we need that value y to be a linear combination of these two vectors, or in other words, it needs to lie in the same plane as these two vectors, right? This purple plane is defining all linear combinations of these two vectors. Now the vector that I'm looking at here, minus 3, 0, 6, if I draw it in here and I actually have to zoom to see it, this is not in the plane, right? So it's not in the same plane as the two columns of our matrix, and so this does not have solutions. All right, so what's a least squares solution? Well, a least squares solution is a solution to a slightly different equation where instead of trying to solve for y, or instead of trying to find a value of x that gives us y when we multiply by a, which is not possible, we look for the closest point to y in the space of things that actually can have solutions. So we project y into the column space of a, and then we solve that. So back to our picture, if we project y into the column space of a, that's really saying that I want to look at this line. So this orange line is representing taking that value of y, the end of y, and looking at the nearest point in the purple plane, which is the column space of a. And when I project it there, I get a new vector, which is going to be y hat, this blue vector here. Let's change our zoom slightly. We can like zoom in here. This blue vector is y hat. Okay, so that's visually what's going on. To solve this, though, we're not going to use this picture, right? That would both be tough in this individual problem, and it would be short-sighted because, generally speaking, we're working in much higher dimensions, and we can't just look at a picture to try to answer things. All right, so how do we actually do this? Well, what you'll have to recall from the projecting into higher dimensional spaces video is that this thing that we're trying to calculate, y hat, when we project onto the column space of a matrix, the way that we do this is by this awful looking calculation, which isn't actually that awful because we always do it using software. I'm going to write this down. So this is the projection onto the column space of A of y. We take y, we multiply by A transpose on the left, and then we multiply by the inverse of A transpose A, and then we multiply again by A. A quick note, this statement that this is true relies on A having linearly independent columns, and in this case, A does have linearly independent columns. It's easy to verify this because we only have two columns, neither of them 0, and they aren't multiples of each other. So this is what we're going to do. And then once we do this, so this is y hat, our value x hat is actually simpler because x hat is A inverse times y hat. So you just get rid of that A at the beginning. It's A transpose A inverse times A transpose times y. All right, so this is what we're going to calculate using software. So let's get away from these awful equations. The nice thing is with software, once you type them in once, you can just reuse that. All right, so for these calculations, we're going to always use NumPy, which simply makes sense. This is an application situation. You're doing this generally because you have real world data. It's rounded values. We're not trying to do symbolic calculations. We want efficiency over exact answers because we recognize that our data is not exact. So the first thing I'm going to do is I'm going to import, if I haven't already, what I need. And then I'm going to enter my matrix and my vector. So I'm going to enter A and I'm going to enter Y. So I've entered them as NumPy arrays. And this doesn't matter so much here because these are simple matrices, but we'll see in the later examples, I'm going to enter them kind of in more, I guess, clever ways. It's always worth just checking that you get the matrix that you wanted. Right? This is one of those easy steps. So I'm just quickly checking that A and Y are in fact the matrix and vector that I wanted. And now to calculate x hat and y hat, I've just typed in here what I have on the iPad, right? So let's add another y hat here. So we have these next to each other. I've just typed these things in, and so I'll calculate them. And then I can look at what they are. So generally speaking, x hat is actually the value that we want, not y hat, because x hat in most situations is representing the coefficients in some sort of equation that's modeling data. But we have the software, we can look at both. So in this problem, we calculate that x hat is, let's write these down. Is 7, -3, and y hat is 1, 2, 4. Quickly looking back at our picture, x hat doesn't show up in this picture. I mean, this is three-dimensional space, and this matrix is representing a linear transformation from two-dimensional space to three-dimensional space. So x hat does not show up, but y hat is this blue vector here. So the vector 1, 2, 4, and so you can confirm if you want that in the x direction it's 1, in the y direction it's 2, and in the z direction it's 4. That's y hat. It's the projection of y onto the column space of A. And just really quickly to summarize what I did in software, the thing that software did for us was make these calculations a little bit simpler. Ultimately, once we know what A and Y are, we always calculate x hat and y hat the same way. In this problem, we could have even done it by hand, right? These aren't even that hard to calculate. We would have had to find the inverse of a 2 by 2 matrix. We would have done a little bit of matrix multiplication. It would not have been so bad. But since we have software, why not? All right, so that was our first abstract application of least squares regression. Let's take this abstract idea and apply it to a real world application. So here, what I'm trying to do is I'm trying to predict a student's exam score from their quiz scores. And the way I'm going to do that is by calling the quizzes X, the exams Y, and trying to create a linear model that predicts an exam score from a quiz score. And the question is, what are M and B? As we saw in the conceptual video, when we start to work this out, we realize that we can't do this, but we don't even really need to do any sort of writing down of equations to see that we can't fit a linear model to this, because this is a picture of a scatter plot of all of these scores, right? The X values are the quiz score and the Y values are the exam score, and you can't draw a straight line through all these points. The linear algebra perspective on this is that if I start writing down these equations, y equals mx plus b, so for student 1, that's saying that 72, and actually I wrote it like this, but because we're writing things as ax equals y, let's just flip this into mx plus b equals y. This looks like, for student 1, 80m plus b equals 72. For student 2, 68m plus b equals 71. And we have 11 equations finishing with 88m plus b equals 92. We don't have a solution to this, right? And when we phrase this in terms of matrices, what we end up getting is that this looks like our matrix A is going to be 80, 68, all the way down to 88 in this column. We're going to have a bunch of ones in this column. We have our matrix X, which is going to be the matrix of coefficients, M and B. And then we have our vector Y, which is going to be all of the exam scores. And thinking of it like this system of equations is the same as AX equals Y, right? When we multiply A times X, we get M on 80, B times 1, so 80 plus B, and then that has to equal 72. That gives us our first equation, and so forth. You'll find that with these least squares regression problems, especially if you're using software, once you have it all set up, there's only 2 things that you need to get right, neither of which is trivial. We've already done the first thing, which is successfully write down what the equations are. That is, successfully convert our problem into matrix equations and write down what the matrices are. So we've written down our matrices, A, X, and Y. The second part is, how do I enter these into the software? So I'm going to just use this exact same sheet. I need to change this part. And I did this earlier because I didn't want to spend the entire video typing this in. That would be pretty unnecessary. I'm just going to copy and paste in these new matrices. And obviously this took some amount of time. We'll see in later examples that we can shortcut this using some tricks of sorts, I guess. And so I'm going to click play. So I'm going to enter these new matrices, and I'm definitely going to print them to make sure that these look like what I want. And this looks good to me. This is the matrix A, this is the vector Y. And once I've done that, I can calculate X hat and Y hat and print them out to see what they are. Again, I printed out y hat, but I don't really care about y hat because y hat is the predicted scores for the students who actually took the exam. That's not really of interest to me. What's interesting to me is x hat. And so I'm going to write that one down. What is x hat telling us? Well, let's go back to the problem. X hat is telling us the coefficients of our linear equation. So this is telling us that the model I should use is y equals 0.739x plus 22.86. So if I have a student's quiz score, the way I predict their exam score is I multiply their quiz score by 0.739, and then I add 22.86 to their exam score. All right, so this example was a pretty, I think, classic linear regression statistics example. I want to change things a little bit to show that it's not, even though this is linear regression and we're using linear algebra, the linearity does not refer to the fact that our model is linear. And I think we'll see with this example what I mean by that. I hope so anyway. The linear, we can model lots of nonlinear things using this sort of technique. All right, so in this example, this is just a contrived example. I wanted some numbers that worked well. So I want to predict the value CI, which I think was supposed to be some sort of confidence index, maybe consumer confidence index, although these numbers aren't, usually the consumer confidence index is more like 100. It doesn't really matter. I'm trying to predict this value, CI, based on the quarter. So each quarter there's a confidence index reported, and I want to model this mathematically. Now, when I go and look at this, so if I plot these on a scatter plot, I see these 6 points, and it doesn't really look like there's a linear pattern here. And this matters a lot when you think about the fact that something like consumer confidence index, you would expect to maybe have some sort of periodic behavior. But I'm not going to do that here because this is just an example that I want to look at. I'm just going to look at this and say, look, this looks like a cubic function. And so I don't want to model this with a linear function. I want to model this with a cubic function. How am I going to go and do that? So if I'm going to model this with a cubic function, my y value is confidence index and my x value is quarter because x is the independent variable. And so I want a model, and let me make sure that I'm consistent with the calculation I'm about to do. I want a model of the form y equals a0 plus a1x plus a2x squared plus a3x cubed. So it's not a linear model, but this is a cubic. This is the sort of thing that I would think would fit the picture that I'm looking at. Even though, as I said, I think it doesn't make a ton of sense in context. Okay, so what you start to realize as you write this down, so first of all, let's do the thing I did before. Let's just change the order of this, be consistent with what we're writing. And as we start to plug in points, so if I plug in the first quarter, x equals 1, and y equals 5. If I plug in the second quarter, y equals 9. And all the way up through in the sixth quarter, I'm going to challenge my ability to do powers of 6 in my head, but I think I got it. We'll see. I get these 6 equations. Again, we're not going to have a solution because, or we shouldn't expect to have a solution because we have 6 equations and 4 unknowns. But notice that when this was a cubic equation, but I was plugging in values for x. And so when I plug in the values, we end up with equations that are linear in the coefficients. And this happens with lots of models that aren't actually linear. As long as the coefficients you're looking for are just coefficients on expressions in your variables, once you take data points and plug in those values, you're going to end up with a system of linear equations that you can apply linear regression to. So I can rewrite this and say, I probably shouldn't have used A, but we're going to go with it. For my coefficients, that is. My matrix A is this. My matrix X, this is where I made poor choices, right? Should have called these things X's or something else, is this. And my matrix Y, this is the only one that was named well. It's all the Y values. And I want to apply least squares regression to this to get a least squares solution for the coefficients. Sorry, I'm just copy and pasting this over. So here I'm going to be a little more creative with how I enter these, and don't worry too much about these details. So it's kind of beyond the scope of this video or this course. So what I'm doing here is I'm noticing that I don't actually need to type this whole thing out. So my data is here, and my Y value is just going to be that, but transposed, right? So if I just enter the data as a list, it'll give me a row vector. If I take the transpose, I'll get a column vector, which is what I want. Now here for A, what I'm noticing is that this matrix has a very clear pattern to it, right? This is 1, 1, 1 squared, 1 cubed, 1, 2, 2 squared, 2 cubed, all the way up to 1, 6, 6 squared, 6 cubed. And so what I'm saying here is using what's known as list comprehension, again, not kind of beyond the scope of this course, but I'm saying, look, each row is 1t, t squared, t cubed for all of the t's between 1 and 6. And in Python, when you type ranges of values, you, for some reason, go one past where you're trying to go. And so I'm doing kind of this clever way. Clever is the wrong word. I'm just saying I'm not typing in all the things. And this is where it's important. I should check this worked, right? I know what I want the matrix to look like. I just didn't want to have to type it all out. And it did work, right? This is the matrix that I was looking for A. And now I print out Y. That's what I wanted for Y. I was pretty sure that was going to work. And again, I can calculate X hat. And I can print out X hat and Y hat. Again, I only care about X hat for the purposes of the calculations I'm going to do. So let's write that down. If the X hat is minus 5.33, 15.07, negative 5.02, and 0.48. And if we look back at the problem, this is saying that the model that I should use is that Y equals the following. So this is my model that relates X and Y based on this data to get a cubic model. So linear regression gave us a cubic model. I want to look at this picture, actually, because I think it's useful to see. So what is this equation? Well, let's draw it on top of the graph. You'll just have to believe me that this is the right equation. This is what we get. And it's always nice to check these sorts of things. This, if you were unsure if this was going to work, it's totally believable from this picture that this is the best cubic you can draw to fit these points from a least squares perspective. Okay, so far, abstract problem, classic linear regression, using regression, linear regression to fit a nonlinear equation. And the final example I want to do is an example where we'll see two things. One, how we deal with maybe really big data sets, but also how we deal with multiple variables. Because it turns out that dealing with multiple variables is really no different from dealing with an equation of this form, for instance. So let's look at that. All right, so in this final example, this example is a bit outdated. We're trying to predict the sales that a company has based on their advertising budget. And the idea is that they have three different ways of advertising. This is the outdated part. They're advertising on TV, on the radio, and in the newspaper. And I'm not sure that radio and newspaper advertising are, that common anymore. I'm not really sure, but this is an old data set. And so in each city that the company operates, they know how much they did in terms of sales, and they also know how much they spent in terms of these three different types of advertising. And they want to get a sense for how they can predict their sales from their advertising budgets. And it's a simple model. It's a linear model, right? We're going to take each advertising budget, multiply it by some constant, and add another constant. Now, our data set is 200 cities. So we're going to have 200 equations. And so it's quite believable that this is going to only be approximate, right? That is, we need some sort of regression. We can't actually solve this. Now, I want to look at the data set. I have it entered over here so that we have a picture of what's going on. So here we can see that we have, for each city, those numbers don't really mean anything. Each city is just assigned a number, right? In this city, we spent $230,000 on TV ads, $37,000 on radio ads, $69,000 on newspaper ads, and the sales were $22 million. I'm not sure if I said that right earlier, but the sales are in millions. Otherwise, this data set represents a company that's spending more than it's making. And so this is just 10 of the cities. There's 200 of these. So if we start writing these down, and so and trying to figure out what's going on, for the first city, we get an equation, right? Their sales, and again, I'll kind of invert this. We'll move the sales to the other side to represent, I guess the equal sign came with it, to represent this the way we've been writing it. For the first city, we have the following. Sorry, I wrote that where you couldn't see it. So this is, we're missing A4. We also have a constant term. So this is what we get for the first city. And then for the second city, we plug in the corresponding numbers. And so forth. So going back to the iPad. So this is kind of what our system of equations looks like. And we can see that our matrix representation, matrix A, is going to be the coefficients. And notice we're going to get this column of ones again. Anytime you have a constant term, you end up getting this column of ones. That's A. X is going to be our 4 coefficients. And Y is going to be our vector of sales. So this is what we get in terms of matrices. Again, this is a lot of the battle. And we have to somehow enter these in successfully into Python so that we can calculate this. All right, so how did I actually do this? I'll just look at the parts of these matrices that we need. I'll copy paste this in. So this is definitely a bit higher level, but you should just be aware if you're starting to work with bigger data sets like this, if you have them in some sort of nice format. So I have this data set in a CSV file. There are lots of ways you can do this in Python. You just need some way of importing it and turning it into a NumPy array for our purposes. And in this case, I'm going to use pandas, which is the Python, one of the really common Python kind of statistics data science packages. So again, the details of how I'm entering this is kind of, I guess, beyond the scope of this course, but basically what I'm doing is I'm taking the CSV file, I'm entering it into Python, and then I'm pulling out the pieces of information I need. And so I'll click play. So don't worry about the details. Let's just confirm that I got what I wanted. So this is the matrix A. I got more than I wanted, but I can look at least the first two rows and say, okay, this was the matrix I wanted for the first two rows. And then we'll scroll all the way down. We can print Y as well. So the first two things in Y were 22.1 and 10.4. That looks pretty good. Okay, and so again, once you have it entered correctly, it doesn't take you any longer, right? It still takes, up to rounding, 0 seconds for Python to do this whole calculation. And I'm not even going to print y hat because it's not that useful to us. It's just going to be another vector of 200 predictions. But x hat I do care about. That's what we're trying to find. And so let's write down x hat and figure out what this tells us in terms of our model. We do have to apply a little caution here. So scientific notation, right? This is saying 0.046, right? We have to move the decimal place 2 to the left. I'll just do everything, I guess, to some number of significant figures. This one's negative 0.001 and 2.939. I'm not really that worried about rounding in this video. So this is what I got out of x hat. And so let's look at what this tells us in terms of the problem. We got to remind ourselves that's A1, A2, A3, and A4. And so this is telling us that this is the equation for their sales. So whatever we spend in TV budget in thousands, we multiply by this. Radio budget times this. Newspaper budget times this. And so forth. Add that up, we get sales. And interestingly, you have to be careful with these sorts of extrapolations, but this is saying that if we spend no money, we'll in a city, we would expect to do 2.9 million in sales. Remember that they're off by a multiple of 1,000. So this is kind of saying that for every dollar in TV spending, we're going to do 46 extra dollars in sales, which sounds pretty good. This is saying that for every dollar in radio spending, we're going to do 189 extra dollars in sales, which is really good. And this is saying that for every dollar we spend on newspaper, we're going to earn $1 less in sales. which is kind of interesting that the newspaper is like almost applying a negative impact on our sales. Now, there's a lot statistically going on there. We shouldn't assume that anything causes anything else to happen. But the step back here is that this process, linear regression, which we're doing from like a very fundamental standpoint, right? We're doing the linear algebra to do it. It does not just apply to the classic statistics linear regression situation where you're trying to predict one variable from another using an equation of the form y equals mx plus b. It's this abstract matrix equation thing that applies in lots of situations. We've just seen a few more examples here where we're trying to use a cubic model and where we're trying to do things with multiple variables, but hopefully seeing those examples, you both understand how to apply this if you encounter a new situation, and also you appreciate how widely applicable this is. That is tons of different ways of writing down an equation for something. You're going to end up with a linear regression situation. That is when you try to set up a system of equations that represents each of your data points being exactly predicted by the model, that you'll end up with a system of linear equations that you can apply a least squares regression to.